Good day everyone, I'm Marcalvin Paloma Montino and I'm here presenting my Week 5 reporting to our HAAWK course in Graduate School, EMG 256, Risk Analysis and Management. So without further ado, let's begin. The report entitled Performance of Passive and Some Active Hazard Barriers Through Physics and Engineering of Failure Modeling, Under Performance Assessment, Data, and Modeling. Many times we are dealing with situations that the performance is better modeled by understanding and modeling the underlying processes and phenomena that apply stress or cause damage and degradation in the unit. This is particularly important in passive system and barrier failures. There are three types of models that can be used to assess reliability, capability, or probability of failure of the various items. These are: first is the stress-strength model. This model assumes that the barrier fails if stress, mechanical, thermal, etc. applied to the barrier exceeds the strength. The stress represents an aggregate of the operating condition and challenges as well as external conditions. This failure model may depend on environmental conditions or the occurrence of critical events rather than the mere passage of time of cycles. The second is the damage endurance model. This model is similar to the stress-strength model, but the scenario of interest is that stress applied causes damage that accumulates irreversibly, as in corrosion, wear, and fatigue. The aggregate of challenges and external conditions leads to the metric represented as cumulative damage. The cumulative damage may not degrade performance. The item fails when and only when the cumulative damage exceeds the endurance. The third one is the performance requirement model. When performance characteristic of a unit degrades to a point that the unit does not meet certain operating and functional requirements, the unit may be considered failed. In this model, a distribution of the performance and its degradation over time is estimated and compared to a fixed value or a distribution of minimum requirement. The probability that performance falls below acceptable minimum requirement is considered as probability that unit fails. Stress-strength models. In this modeling concept, a failure occurs when the stress applied to an item exceeds its strength. The probability that no failure occurs is equal to the probability that the applied stress is less than the item's strength. The formula is stated in 494, where R is the reliability of the item, small s is the applied stress, and big S is the item strength. Examples of stress-related failures include application of extra load to a pressure vessel, such as compressed natural gas container. Engineers need to ensure that the strength of an item exceeds the applied stress for all possible stress situations. Traditionally, in the deterministic design process, safety factors are used to cover the spectrum of the possible applied stresses. This is generally a good engineering principle, but failures occur despite these safety factors. On the other hand, safety factors that are too stringent result in over-design, high cost, and sometimes poor performance. If the range of major stresses is known or can be estimated, a probabilistic approach can be used to address the problem. This approach eliminates over-design, high costs, and failures caused by stresses that are not considered early in the design. If the distribution of big S and small s can be estimated as F of S and G of S, then Figure 4.9 shows Fs and Gs distribution. The safety margin Ms is defined as the Sm shows the relative difference between the mean values for stress and for strength. The larger the Ms, the more reliable the item will be. Use of 4.96 is more objective way of measuring the safety of items. It also allows for calculation of reliability and probability of failure as compared with the traditional deterministic approach using safety factors. However, good data on the variability of stress and strength are often not easily available. The distribution of stress is highly influenced by the way the item is used and the internal and external operating environments. The design determines the strength distribution and the degree of quality control in manufacturing primarily influences the strength variations. It is easy to show that for a normally distributed big S and small s, where F times Sm is the cumulative standard normal distribution with Z is equal to Sm. See Table B.1. Example 4.16. Consider the stress and strength of a beam in a structure represented by the following normal distribution. What is the reliability of this structure? Solution. With Z is equal to 1.4 and using table B.1, R is equal to 0.91. Example 4.17. A random variable representing the strength of a nuclear power plant containment building follows a log normal distribution with a mean strength of 0.905 MPa and a standard deviation of 0.144 MPa. Four possible accident scenarios can lead to high pressure conditions inside the containment that may exceed its strength. The pressures cannot be calculated precisely, but can be represented as another random variable that follows a log normal distribution. A. For a given accident scenario that causes a mean pressure load inside the containment of 0.575 MPa with a standard deviation of 0.117 MPa, calculate the probability that the containment fails. B. If the four scenarios are equally probable and each leads to high pressure condition inside the containment with the following mean and standard deviations, calculate the probability that the containment fails. And this was the given. C. If the containment strength distribution is divided into the following failure mode contributors with the mean failure pressure and standard deviation indicated, repeat part A. Solution. If S is a log normally distributed random variable representing strength, and L is a log normally distributed random variable representing pressure stress, then the normal variable Y is Ln times S minus Ln times L is also normally distributed. For the log normal distributed with the mean and the standard deviation of My and Sy, the respective mean and standard deviation of the normal distribution Mt and St can be obtained using 8.47 and 8.48. Then, the formula would be like this. A will be R is equal to 0.9642. The probability of the containment failure, F is equal to 1 minus R is 0.0358. Because of the four scenarios are equally probable, then the system is equivalent to a series system such that R is equal to R times R2 times R3 times R4. And this will be the values of R1 to R4. The probability of containment failure, F is equal to 1 minus R, is equal to 0.2297. C. Because each failure mode may cause a system failure, this case can be treated as a series system. Because we know the mean of the log normal distribution using the same procedure used in part A and B, we have these values. The probability of containment failure is equal to F times 1 minus R is equal to 0.0122. If both the stress and strength distributions are exponential with the parameters Ls and Ls, the reliability can be estimated as this formula from 4.98. For more information about stress-strength models in reliability analysis, the readers are referred to O'Connor and Kapoor and Lamberson. Damage endurance models. In this modeling technique, failure occurs when applied stress causes permanent and irreversible damage as function of time. When the level of damage reaches a level that the item is unable to endure, the hazard barrier fails. In practice, damage and endurance are not precisely known. They may be expressed as PDFs at best. Damage accumulation does not always occur in the same way. and different initial condition may result in drastically different damage. Endurance limit is not the same as well, because the strength of the material varies from unit to unit, and endurance is considered as a characteristic of material. In any case, failure occurs only when the accumulated damage exceeds the endurance limit of the material. The interference of variability and uncertainty in accumulated damage and endurance limit and occurrence of failure are illustrated in Figure 4.10. This figure shows how the interference of damage and endurance make a statistical distribution of TTF, which is the variable of interest in most of the reliability analyses. Figure 4.10, the Damage Endurance Modeling Model. The problem is to establish a distribution of damage and endurance as a function of time. Clearly, as we are unable to reduce all the uncertainties involved in measuring damage and endurance, they are often represented by PDFs as shown in Figure 4.11. The mathematical concept determining the reliability of the hazard barriers at a given time is similar to the strength-strength model approach, and also apply to damage endurance model at a given age of a cycle of operation. Clearly, the stress distribution is now represented by damage distribution, and strength distribution is represented by endurance distribution. Figure 4.11, Impact of time on damage endurance modeling. To estimate damage and endurance distribution, we need to understand the degradation process leading to damage and reduction of endurance limits, and perform engineering-based degradation analysis. Degradation analysis involves the measurement of degradation as a function of time, relating degradation rate to time, and ultimately life and determining the acting failure agent. Many failure mechanisms can be directly linked to degradation agents, and enable the analyst to assess probability of failure of the hazard barrier at any time in the future by extrapolation. Further, tests at elevated stress level can be performed, which speed up the degradation and damage process. The degradation and stress tests can provide the information of assessing the distribution of TTF of the barriers. For more information on this subject, the readers are referred to Nelson. Once the level of endurance is defined, the degradation over time should be measured. The uncertainty in the results is directly related to the number of items and amount of data obtained in the observations at each stress level, as well as in the amount of overstressing with respect to the normal operating conditions. The degradation of these items needs to be measured over time, either continuously or at predetermined intervals. Once this information has been recorded, the next task is to extrapolate the measurements to define failure level to estimate the failure time. These models have the following general forms, where the Y represents the performance, X represents applied stress, level of damage, or level of requirement, and A and B are model parameters to be estimated. As illustrated in Figure 4.12, using the engineering of failure model with one wear agent, one can significantly simplify an wear problem and life estimation, instead of dealing with many variables and conditions, as only one value represents the aggregate effects of all others. In this figure, clearly degradation life model in form of 4.101 is used and plotted in log-log scale. The degradation analysis using engineering principles shows that the maximum shear stress in the vicinity of the surface is an aggregate agent of failure responsible for material removal in the abrasive wear process. The wear rate can be expressed as a power relationship similar to 4.101. Having the wear rate, life of the bearing can be estimated by considering an endurance limit beyond which the bearing can be considered failed. This end state can be defined either based on the surface roughness or a certain amount of material removal on bearing. Based on the above description, the damage of the bearing can be related to the wear agent as. Therefore, the formula will be like this, where W is the wear rate, CO the end state where C the constant, L, D, the life and damage of the bearing in terms of thickness removed, dependent variable, K, N, the constant to be estimated from the accelerated test result, TYP, the material shear yield point, and the Tmax, the maximum shear stress in the vicinity of the surface, independent variable. Note that the presence of TYP enables this model to also consider the temperature degradation of the bearing material, which can be critical for coated type bearings. Assuming that the life is distributed log normally, then the joint distribution of life stress can be obtained from 4.103. As U is the mean of the natural logarithms of the TTF is equal to negative ln times k minus n times ln Tmax. Therefore, 4.104 will be like this. Example 4.18. A2024 T3 all competent was fatigue tested to failure at two different cyclic stress levels of 400 and 450 megapascal, and the following data were observed. Estimate the number of cycles to failure at 300 megapascal. Solution. Assuming that fatigue damage mechanism leads to cycles to failure that follows a log normal life distribution and an inverse power relationship for the stress life model similar to 4.104, then the formula where n represents cycles to failure, Sn, the standard deviation of the natural logarithms of the cycle to failure, and k, and the power of law model parameters. The parameters are calculated through the MLE approach. K is equal to 0.2. Then the mean life of the conditional joint cycle and stress log normal life model at the stress level of 300 megapascal is calculated from the expected value expression for the log normal distribution as T is equal to 134.2 cycles. And that is the end of my reporting. Thank you and have a good day.